Okay, so now let's have some fun with the graphical calculator. We would go to the front end again, and let us see what happens if we change this to p-type. And this to n-type. And there we see the band diagrams now. Um, First, let's look at the green one, where the EF on the left side is closer to the EV, and the EF on the right side is closer to EC. So this is p-type and this is n-type. In this case, the charge density signs would have been reversed, and so the electric field is now negative, and so the potential is dropping, and that's what we see in the band diagram as well, where where at the junction the energy levels are gradually dropping. Now, let us say if we reduce the doping concentration on the left-hand side by an order of magnitude. You would see the graphs change, and you would see that the width of the depletion region on the left side would now be more than the width of the depletion region on the right hand side. And this is something that would be confirmed in the plots of the charge density, the electric field, and the potential. And what happens if we increase the doping concentration on the left-hand side by an order of magnitude compared to 1 exponential 15? So as we would expect, this would be opposite. The energy levels are going to drop in such a way that the P side width of the depletion region is much less than the width of the depletion region on the N side, or in this case, the right-hand side. And this is also verified by the plots of the charge density, the electric field, and the potential. So in essence, you can play with this calculator by changing the n-type or the p-type on the left side or the right side, and using various doping concentrations. So we'll do one more. And this time, let's reduce the doping concentration of the left-hand side by an order of magnitude 2 compared to 1 exponential 15. So we'd go down to 1 exponential 13. And you can see that we take some time before the graph actually shows up, and that's because you can see these calculations that are going on. Remember that we have about 500,000 rows, so these calculations take some time before the values change, and you can see the change in the graph then. So now obviously the width of the depletion region on the left hand side is much more than the width of the depletion region on the right hand side, and you can see the same coming up in the graphs of the charge density, the electric field, and the potential. And what happens if we change this, the left-hand side to N-type, keep the same doping concentration, and change the right-hand side to P-type with the same doping concentration. And once again, you can see the Excel is starting to do the calculations right now. Right here on the screen, it takes some time. And then once it's done, you'll see the change take place in the graphs. There we go. And the same being reflected in the graphs of the charge density, electric field, and the potential. Now, one of the things that we should caution is that given that our increments of x-axis is in 0.01, if the width of the depletion region becomes less than 0.01, then we would miss points for the calculations of charge density on the left side or the right side, depending on which side is less than 0.01 micron, given the doping concentration that the user might put. And so those points would miss out in the electric field and the potential, causing possibly errors in the final outcome of the band diagram. But as long as the width of the depletion region is greater than 0.01, the graph gives a good appreciable shape of the band structure.